Hello, everyone. Welcome back. Today, I'd like to review with you Chapter 5, which is focused on circular motion, the planets, and gravity. Let's share my screen. So, after going through this chapter together, I'd like us to be able to describe the acceleration due to a change in the direction of the velocity vector. This is also known as centripetal acceleration or center-seeking acceleration. And as we learned in Chapter 4, if there's an acceleration, there must be a force that causes that acceleration. So we're going to describe forces that can act as centripetal forces. And we are going to apply Newton's laws to objects that are moving in circular motion. And lastly, we'll analyze planetary motion. So as mentioned, this chapter focuses on circular motion, the planets, and gravity. So I showed two pictures here. One of the Earth. We know that the Earth revolves around the sun. Other planets revolve around the sun. Their paths are not completely circular, but they're pretty close to being circular, actually. And then in the other picture, I show a car that has been unable to navigate a bend in the road. And you might wonder how these two pictures are related at all. Well, in both situations, there's an object undergoing circular motion. And there are forces involved for these objects to go in a circle. And so if the forces are holding steady, the object will continue to move in a circle or a circular path. However, if you don't navigate the bend in your car, there was not enough force to keep you accelerating around that curve. But we can apply the same physics principles for both situations. So let's just visualize what's happening in circular motion. So we have an object moving in a circular path. Let's suppose we're looking at this top-down view. Now the center of the circle is shown in red, and this vector called r is pointing from the center of the circle out to where the object is in space. And the blue vector that's denoted with a v stands for the velocity vector. Notice that the length of this blue vector, this blue velocity vector, is not changing. So that means the magnitude of the velocity is not changing. If this object is moving at 10 meters per second, it's moving at 10 meters per second everywhere in the circle. So it's going at constant speed in a circle. However, the object's velocity vector is changing as time passes. It's pointing to the left when it's at the top. It's pointing to the right when it's at the bottom. So the direction of the velocity vector is changing. This is an important concept because even though the object is moving at a constant speed in a circle, it is still accelerating. The reason for the acceleration is that the direction of the velocity vector is changing with time. So acceleration can occur in a couple of different ways, right? I can speed up, right? I can go from 10 meters per second to 20 meters per second, and that would involve an acceleration. That happens when the magnitude of the velocity changes. The other way that we can have an acceleration is when the direction of the velocity vector changes, as shown here. So that's happening when something is moving in a circle. This is what's called centripetal acceleration. This is the rate of change in the velocity of an object that is associated with the change in the direction of the velocity vector. This centripetal acceleration, centripetal means center seeking. So this acceleration points towards the center of a curve. If I'm looking at a circular path, that acceleration points towards the center of the circle. So it would point inward here. At this point, it would point inward towards the center of the circle here. It's perpendicular to the velocity vector. If I'm going at a constant speed in the circle. And notice if I wanted to find a direction in the change in the velocity between these points, point 1 and point 2 in the circle, I do v1, velocity at point 1, minus the velocity at point 2, I would get this vector right here, delta v. And it's pointing towards the center of the circle. That means that the acceleration vector points towards the center of the circle. To quantify the centripetal acceleration, the size of the centripetal acceleration depends upon the velocity of the object and the radius of the circle or the curve. And in particular, the magnitude of the centripetal acceleration, I'll denote that A with the subscript C, is equal to the magnitude of the velocity squared divided by R. Why is it V squared divided by R? Well, the acceleration is directly proportional to the velocity squared. Right? So there's two effects from the velocity that are causing the acceleration to increase here. If the speed of the ball or the object that's moving in a circular increases, the velocity vectors become longer, and that means that delta V vector becomes longer. Obviously, that's going to create a larger centripetal acceleration pointing towards the center of the circle. If this is becoming longer, the acceleration becomes longer. In addition, the greater the speed, the more rapidly the direction of the velocity vector changes. So, centripetal acceleration depends upon velocity, and in particular, its velocity squared because of those two effects. It's inversely related to the radius of the circle. As the radius of the curve decreases, the rate of change in the velocity increases because the direction is changing more rapidly. A tight curve produces a large change in the velocity and therefore a large centripetal acceleration, but a gentle curve produces a small change in the centripetal acceleration and a small change in the velocity. That's why it's easier to navigate bends with larger radius. Notice that the unit for centripetal acceleration is meter per second squared. We learned before that the units for acceleration is a meter per second squared, and the same thing is happening here. I've got a velocity squared on the top, meter per second squared on the top, and the unit for the radius is also a meter. So I got meter squared divided by meter. That gives me a meter, and I have seconds squared on the bottom. So the units for centripetal acceleration are also meter per second squared. So I have a question for you. You are twirling a ball on the end of a rope in a horizontal circle above your head. Double the speed at which the ball is moving. What happens to the acceleration, centripetal acceleration? Is it doubled? Is it halved? Is it increased by a factor of 4, decreased by a factor of 4, or not enough information? Pause the video, make your selection, and then we'll talk about it. It's actually increased by a factor of 4. Remember, centripetal acceleration is v squared. If I double the speed, I double the magnitude of the velocity, the new centripetal acceleration is going to be 2 times the original speed squared. This is my new velocity, and I square it, and then I divide by r again. This becomes 4 v squared over r. This is 4 times the original centripetal acceleration that I started with before I doubled the speed. Same situation. You're twirling a ball on the end of a rope in a horizontal circle above your head. You double the radius of the circle in which the ball is moving. What happens to the centripetal acceleration? It is doubled, it is halved, it is increased by a factor of 4, it is decreased by a factor of 4, or not enough information. Pause the video, choose your answer, and then we'll talk about it. It is halved. So remember, centripetal acceleration is v squared over r. This is my original centripetal acceleration. If I double the radius of the circle, the centripetal acceleration becomes v squared over 2r. Centripetal acceleration has become halved. Half as much as it was originally. Another conceptual question for you. Suppose you're twirling a ball on a rope in a horizontal circle above your head. The rope suddenly breaks. In which direction is the ball going to travel? So let's suppose this is a top-down view. It's moving, the object is moving in a horizontal circle, and it's, being twirled this way, and the rope breaks at point A. After the rope breaks, which direction is the ball going to go? Is it going to fly out? Is it going to go in path 2? Is it going to go along path 3? Or is it going to go along path 4? Think about it for a second. Pause the video, choose your answer, and then we'll talk about it. The correct answer here is that it will travel along path 3. We're looking at this from a top-down view, and the string breaks right here. The ball is going to move in the direction that it was moving when the force disappeared, in accordance with Newton's first law of motion. So notice, as this animation is showing on the right-hand side, if the string breaks right there, what is the direction of its velocity? Tangent to the path. It breaks right here, the velocity is pointing this way. Once the string breaks, there's no more force keeping it moving in a circular path. And Newton's first law says that if there's no net force acting on the object, it's going to be either at rest or move at a constant velocity in a straight line. And so that's the way it's going to be, right? It's going to just continue moving in a straight line at a constant velocity after the string breaks. Now, if there is a centripetal acceleration, okay, that we learned in chapter 4, if there's an acceleration occurring, that means there has to be a net force acting on an object to cause it to accelerate. That's Newton's second law. Same thing happens with centripetal acceleration as well. If there is a centripetal acceleration, there must be some force causing this acceleration due to Newton's second law of heaviness and weight. Now, this force could be the tension in a string twirling a ball, like we've been looking at these different animations with the ball moving around in a circle that's tied to a string. The tension in the string is the force that's causing the centripetal acceleration, that's causing the ball to twirl around in a circle. But another example of a centripetal force could be the friction between the tires and the road while the car goes around the bend. In order to navigate a bend, there has to be enough friction between your tires and the road to make that turn. And so the friction is the centripetal force that causes the centripetal acceleration to occur. Another example of a centripetal force could be the gravitational force between two planets. The Earth experiences a gravitational force from the sun, and it's directed directly towards the sun. Therefore, the Earth has a centripetal acceleration that points directly towards the sun, and it moves in an almost circular path around the sun. Some people are very tempted to call centripetal forces its own force, but it's not its own force. There are examples of things that can act like a centripetal force, but it's not its own unique thing. Tension, friction, gravitational force are all examples of a force that could be called a centripetal force that creates a centripetal acceleration. So, what helps a car navigate a curve? We have already talked about this a little bit, but obviously the frictional force between the car's tires and the road. Notice this car moving around a bend. This is looking like a circular, curved path. It's part of a circular path. The acceleration vector, centripetal acceleration vector, is going to point towards the center of that circular path. Therefore, the force, the centripetal force, also has to point towards the center of the circular path. And in this case, the centripetal force that's causing that centripetal acceleration is the frictional force between the tires and the road. Another example of a centripetal force that helps a car go around the bend is a banked curve. So if you've ever been to a racetrack where at the ends of the racetrack, you notice that the road bends, is banked, as kind of shown in this picture right here. This is showing the normal force from the road acting on the car. It points perpendicular to the surface. That's this one right here. And if I break that normal force up into its vertical and horizontal components, notice that the horizontal component could also be a force that helps a car go around the bend. So if I'm moving around the bend, and this is my road right here, my centripetal acceleration has to point towards the center and navigate this bend. The normal force horizontally can provide an additional centripetal force pointing towards the center of the circle, causing the centripetal acceleration to occur. You see banked curves often on high-speed highways, right? Because you're moving at a much faster speed. Your centripetal acceleration would be very large going around these bends. So in addition to friction between your tires and your road, this normal force, this additional normal force, can help you navigate these bends safely without losing traction with the road. Conceptually, which of the following actions would make navigating a bend in your car more difficult? Going at a higher speed, if the bend has a larger radius, if the road was slippery. Going at a lower speed, if the bend has a small radius or if the road was steep. Think about it for a second. Which of these would make navigating a bend in your car more difficult? Pause the video, make your selection, and then we'll discuss. Going at a higher speed, that's one of the ways in which it would make navigating the bend in your car more difficult, because if you're going at a higher speed, the magnitude of your velocity is increasing. That means the centripetal acceleration is also going to go up. And you're going to need a lot more centripetal force to allow you to navigate that bend safely at that, to have that centripetal acceleration. If the road was slippery, that would also make it more difficult because there would be less frictional force between your tires and the road. That may lessen the amount of centripetal force there to allow you to stay on the road, and so you could lose traction. If the bend has a small radius, remember radius and centripetal acceleration are inversely proportional. So if it's a small radius, then centripetal acceleration is going to go up and be large. And again, if I have a large centripetal acceleration, I've got to have a large centripetal force to keep me in that circular path. If the bend has a large radius, that's going to reduce my centripetal acceleration, making it easier to navigate. Going at a lower speed will also make it easier to navigate. And if the road is bent, that's going to provide me with an additional centripetal force, allowing me to have a larger centripetal acceleration. So those are some of the concepts behind centripetal force and centripetal acceleration. Now, one area where you may have experienced centripetal forces in your everyday life, well, not everyday life, but maybe during the summertime, when you go to the amusement park, when you ride a Ferris wheel. Have you ever felt that very heavy feeling when you get to the bottom of the Ferris wheel? You feel like you're being pushed into the seat. And at the top of the Ferris wheel, when you go over the very top, you get that light sensation when you feel like you're almost leaving the seat. This phenomenon can be explained by thinking about the centripetal force. So if I look at the bottom, let's analyze the forces on you at the bottom, and let's use Newton's second law to analyze it. So F net, the net force acting on you at the bottom is equal to your mass times your acceleration. What are the forces that are acting on you at the bottom? Well, there's your weight pulling down on you, and the normal force from the seat acting upward on your body. Okay, so I will call normal force upward, and it's positive. Weight is acting downward on you, so it's minus. The centripetal acceleration always points towards the center of the circle. So that's pointing upward, so that's going to stay positive. This side becomes positive mass times centripetal acceleration. What I'm going to do is solve this for the normal force. Normal force is equal to weight, the weight plus m times the centripetal acceleration. And I'm just going to substitute the expression for centripetal acceleration, v squared over r here. So at the bottom, the normal force that you experience from the seat acting on your body has to take into account not only your weight, but also the fact that you are experiencing an acceleration pointing towards the center of the circle. So at the bottom, you're going to feel heavier because what you feel is actually the seat pushing into your body, that normal force. And so if the normal force is greater than your weight, you're going to feel heavier. Let's think about what happens at the top. Again, we're going to get from Newton's second law, F net equals ma. At the top, let's draw our forces. I've got normal force from the seat acting on my body that points upward. I've got the gravitational force, or my weight, acting downward. Centripetal acceleration always points towards the center of the circle, so here it's pointing down. So on the left-hand side, the forces are the normal force acting up, the weight acting down. And here, the acceleration is acting downward because it's centripetal acceleration pointing towards the center of the circle. I'm going to make that negative since it's pointing down. So again, solving for normal force, that's the force that your body feels from the seat acting on you. It's your weight minus mass, centripetal acceleration. And I'm going to substitute v squared over r for centripetal acceleration. So notice that the normal force at the top is your total weight minus mv squared over r. So the normal force is less than your actual weight. Force that the seat exerts on your body is less than your weight. So that actually makes you feel lighter at the top. Get that light sensation in your body when you go to the top of the hill. So just an example where centripetal forces and centripetal acceleration come into play. Let's practice this a little bit mathematically. Let's suppose we have a ball of mass 0.05 kilogram. It's revolving at the end of a string in a horizontal circle with a radius of 40 centimeters. The ball moves with a constant speed of 2.5 meters per second. What is the centripetal acceleration and what tension is needed to produce this acceleration? I'd like to write down our givens. The mass of the ball is 0.050 kilograms. The radius that it's traveling in is 40 centimeters. If I convert that to meters, that's 0.40 meters. Its speed, the magnitude of its velocity, is 2.5 meters per second. Centripetal acceleration is v squared over r. Magnitude of the velocity is 2.5 meters per second. I square it, and then I divide by the radius of the circle, 0.40 meters. Centripetal acceleration is going to be 15.6 meters per second squared. Next part is asking what is the tension needed to produce this acceleration. I'm doing a top-down view of this. Here's my ball, say for example at this point. Moving at a constant speed in the circle. Acceleration points towards the center of the circle. We've already solved for the size of that acceleration is 15.6 meters per second squared. That means that there must be a tension force from the string acting on the ball that also points towards the center of the circle. Finally, the second law, F net equals ma. The forces that are acting radially in the circle are the tension force. Obviously, gravity would also be acting on the ball as well, but it's acting downward on the ball, right? If I'm looking at a top-down view, gravity would be pointing down on the ball, kind of like into the board. That's not going to be contributing to the centripetal acceleration here, right? Because it's in a totally different direction. Since we don't include the force of gravity here. The tension in the string is what's causing the ball to move in a circular path. And that's the only force that's acting radially here. So we'll put tension here. And it has to be equal to mass times the centripetal acceleration. The tension force here is the centripetal force. Causing the centripetal acceleration. So let's plug in our values. Mass of the ball is 0.50 kilograms, and the centripetal acceleration we just solved for 15.6 meters per second squared. So the tension force here is 0.78. Remember the units for force? Tension is a force, the units would be newtons. And we found the tension required to produce this acceleration. I have a couple of more conceptual questions for you now. Choose all of the following statements that are correct about an object moving clockwise in a circle at constant speed. The object is not accelerating. The object has no net force acting on it. The velocity of the ball is not changing, or none of the above. Think about these statements. Choose your answer. Pause the video, think about it for a second, choose your answer, and then we'll discuss. The correct answer here is none of the above. If you've got an object moving at a constant speed in a circle, the object is accelerating, right? Its velocity vector direction is changing. That means it's accelerating, and it has a centripetal acceleration. If it has a centripetal acceleration, it must have a net force acting on it. The second law, F net equals ma. Even if the acceleration is centripetal acceleration, there's still a force acting. The velocity of the ball is not changing. That is false. The magnitude of the velocity is not changing, but the direction of the velocity is. Therefore, the velocity of the ball is changing. Another review question for you, just to make sure you get all these concepts down. Choose all of the following statements that are correct about an object moving at a constant speed in a circle. The object has an acceleration that points inward towards the center of the circle. The acceleration of the ball increases as the speed of the ball increases. The acceleration of the ball increases as the radius of the circle increases. The object has a net force on it that points outward from the center of the circle. Pause the video, choose which options you think are correct, and then we're going to discuss together. Only the first two statements are correct. The object does have an acceleration that points inward towards the center of the circle. That's the centripetal acceleration. As the speed of the ball increases, the acceleration is going to also increase. Remember, centripetal acceleration is v squared over r. If the radius of the circle increases, the centripetal acceleration of the ball is going to go down. These are inversely proportional, acceleration and radius. And then the last statement is false because the net force on the object must point inward towards the center of the circle. because the acceleration points inward towards the center of the circle. Now this question gets confusing for some people because they often recall the experience of going around a bend in a vehicle, and it often feels like you're being thrown outward, or you're kind of being thrown into the door or pushed outward from the center of the circle. The reason why you feel that way is because you are in the frame of the reference of the object that is actually accelerating. So the reason that you feel like you're being pushed outward is really because if you were looking as an outsider looking in on the vehicle, you would see that the car is pushing on you. The car door is actually pushing on you, keeping you going along with the car in the circle, right? But since you're in the vehicle, you don't recognize that you are accelerating that way. You just feel like you're being thrown out and there's some force that's throwing you out. In reality, it's the car door that is the thing that's pushing on you, keeping you going in the circular path. If the car door wasn't there, you wouldn't fly outward from the center of the circle, you would fly forward, kind of like that example with the string that breaks, right? If the car was right here and you know the car door wasn't there, you just fly forward. You would not fly outward. So it has to do with the frame of reference you're in. We are going to think of all of these questions from the frame of reference outside the thing that is rotating to make our life easier. So I'm wondering if you've ever seen this demo before, where you put water in a bucket. You spin it over your head and the water doesn't fall out. And the question is, why doesn't the water fall out? Again, we can analyze this using Newton's second law and centripetal acceleration. Let's think about the forces that are acting on the water in the bucket. So let's draw this. I'm going to draw it when the water is at the top of the path. Here's the water inside the bucket. I will draw the string. Here we are at the top of the path. We want to look at the forces that are acting on the water in the bucket. The forces that are acting on the water, well, obviously we have the weight of the water acting downward. There's another force that's acting on the water as well, and it's the force from the bucket acting on the water. It's kind of like a normal force from the bucket's base acting on the water itself. I will draw that here as well. There's two forces acting on the water, and at the top of the path, the centripetal acceleration of the water is towards the center of the circle. So let's apply Newton's second law here. Everything is acting downward, so I'm going to make everything negative. There's the normal force of the bucket acting on the water. There's the weight of the water acting down. And then the centripetal acceleration acts downward. Everything is negative, so actually I can multiply through by -1 and make everything positive. And what I'm going to do is, again, I'm going to solve for the normal force. Now, in order for the water to remain in contact with the bucket, the normal force has to be greater than 0, right? It has to be, if it's 0, if the normal force between the water and the bucket becomes 0, that means the water is losing contact with the bucket, and there's no more force between them. So the normal force has to be greater than 0. So that means this term has to be greater. I'm going to write these out a little bit in more detail. So mass times the centripetal acceleration, which is v squared over r. Weight of the water in the bucket is equal to the mass of the water in the bucket times g. Notice that mass is in both terms, so I can cancel it out. V squared over r, or our centripetal acceleration has to be greater than g, 9.8 meters per second squared. Well, what does that mean? What it means is the bucket has to be falling faster than the acceleration due to gravity g. The bucket has to be falling faster than the acceleration due to gravity. What does that mean? If the acceleration of the bucket is less than g, you're not going to be spinning it fast enough, and the water will fall out. You will lose contact between the water and the bucket. If you are spinning the bucket such that it's moving faster or accelerating greater than 9.8 meters per second squared, the water will stay in. The water wants to fall at a rate of 9.8 meters per second squared down towards the Earth. If the bucket is accelerating faster than that, down towards the center of the Earth, so if the bucket has an acceleration of 15 meters per second squared, it's going to be accelerating down faster than 9.8. So that means the water will stay in. Water will stay in. It's kind of like if you were in an elevator, and all of a sudden the elevator starts accelerating downward at 15 meters per second. Well, you're only going to fall at 9.8 meters per second. You're in free fall. So what's going to happen? If the elevator is accelerating faster than you're going to get jammed up on top of the elevator, right? Same thing's happening here. The water is getting jammed up on top of it. I hope that makes sense. That's why the water doesn't fall out. That's also the physics behind, inverted loop-de-loops on roller coasters, right? And why you don't fall out. And you're upside down at the top. Last part of this chapter now deals with planetary motion. So how can we use all of the concepts that we have learned about involving centripetal acceleration, centripetal force, Newton's laws, and apply them to planetary motion? Because planets are moving in almost circular paths around the sun. Their paths are elliptical, okay, but they're not very stretched out ellipses. They're more closer to being a circle than we realize. So animation shows, it's not to scale obviously, but this little animation shows the sun at the center, then you have all the planets. Also shows the moons of the planets. There's a couple different things to note here. The planets are moving in elliptical shapes or almost elliptical shapes. And as you get further out, away from the sun, notice that the planets are moving slower and slower and slower. So I think Saturn, here's Saturn. I think Saturn has it takes Saturn, I'm probably stating the wrong fact right here, but I believe Saturn takes 88 years, 88 Earth years to go around the sun. The time it takes for you to go around the sun increases as you get further away from the sun. One of the scientists who investigated the planetary motion was Kepler, and he actually came up with 3 laws of motion, of planetary motion. The first law was that planets' orbits are ellipses. An ellipse is showed here. If you want to draw an ellipse, you take a string, tap it down with 2 little points right here, and then take your pencil and draw all the way around like this. Stretch the string and draw all the way around. That'll be an ellipse. And notice that the length of the string that you use stays constant as you go around. These little points right here, this one and this one, it's called a focus. And so when a planet goes around the sun is actually at one of these focuses. So the sun could be over here, and maybe this is Earth traveling around the sun. Again, this is a very stretched out ellipse. Earth's orbit is almost practically circular in nature, but it's slightly stretched. So we say that it's an ellipse. So that was his first observation. The orbits of the planets are ellipses. His second law states that planets actually move faster when they are closer to the sun, and they move slower when they are further away. And this little animation is showing what's being stated in words up here. So an imaginary line joining a planet and the sun sweeps out an equal area of space in equal amounts of time. So if this is the Earth going around the sun, maybe from here to here is 1 month. And then from here to here is 1 month. And here to here is 1 month. Equal amounts of time. Each of these areas, right? The area here and the area here is the same area. Same as the area here, same as the area here. So in order for that to happen, it means that the planet must be moving slower when it's further away because it's sweeping out a lot of area out here. And it has to be moving faster over here to match the same amount of area to the spaces. Faster when you're closer, slower when you're further away. The third law that Kepler discovered, I guess, is that if T is the time period taken for the planet to complete 1 full orbit around the sun, and R is the average radius of the distance of the orbit around the sun, then the ratio of the square of the period to the cube of the radius is the same for all planets. That's what, right? What is that saying? Notice that suppose the yellow one is the sun, and then these two out here are different planets, right? The inner one has a small radius. That means it also has a smaller period. It takes shorter amount of time to go around the sun once. It's going around it faster. On the other hand, the red planet out here, it has a larger radius. And it also takes a lot longer to go around. So what Kepler did was basically he tracked, like, what is the period of Earth? What is the period of all the other planets? He was able to do that amazingly enough back then. So he tracked their period. And he was able to determine the distance of each planet from the sun. And he looked at, is there any relationship between these for each of the planets? And what he finally saw was that if he plotted t squared and r cubed on a graph, that it would be, he got a nice linear relationship when he did that for all the planets. Got a nice linear relationship. And so that means that, you know, if I tell you, if I know the period for Jupiter, I can tell you how far Jupiter is away, because I know what the period for Earth is and the radius for Earth is. It has to be the same ratio as it is for the period squared over r cubed for Jupiter. It's the same for all planets. T squared over r cubed for Jupiter, for example, is the same ratio as t squared over r cubed for Earth. They all have the same ratio. Okay, so quick review. Where is the planet moving fastest in its orbit around the sun? Pause the video, give it an answer. Yes. Oops. Guess I didn't have to put the answer here. The planet is moving fastest in its orbit around the sun when the planet is closest to the sun. Remember our little animation here. It's going slow. When it's further away, and it starts speeding up, speeding up, speeding up. And gets faster. Another question for you. Choose all the following statements that are correct about Kepler's laws of planetary motion. A planet moves fastest when it's farthest from the sun. Orbits of planets are circles. If a planet's average distance from the sun is 2 astronomical units. And by astronomical unit, 1 astronomical unit is the average distance from Earth to sun. So in astronomy, they often just call it 1 AU, is 1 astronomical unit. It's the average distance from the Earth to the sun. So if the planet's average distance from the Earth to the Sun is twice or 2 astronomical units, the planet's time of orbit is the square root of 8 Earth years. If the planet's time of orbit is 2 Earth years, the planet's average distance from the Sun is 4 AU. Think about each of these statements for a second. Decide which ones you think are true. We'll discuss in a minute. The correct answer here is 3 only. The planet does not move fastest when it's farthest from the Sun. It moves fastest when it's closest to the Sun. The orbits of planets are ellipses, not circles, although they are pretty close to circles, but they aren't truly ellipses. If a planet's average distance from the Sun is 2 astronomical units, the planet's time of orbit is square root of 8 Earth years. Let's actually work this one out. So this involves Kepler's third law, this t squared over r cubed thing. So t squared over r cubed for the planet, whichever one it is, has to be equal to t squared over r cubed for Earth. The ratio is the same for all planets, whether it's Earth, Jupiter, Saturn, whatever. This ratio always ends up being the same number. So the planet's average distance from the Sun is 2 AU. So that's R. That's R for the planet. We're trying to determine the planet's time of orbit. So let's keep that one in. Should be putting cube on the top. Let's see. The distance of the planet to the Sun is 2 AU. We have to cube. T squared over r cubed for Earth actually becomes 1 because its period, the period of Earth is 1 Earth year, right? So 1 Earth year. And the distance from the Earth to the Sun, we said, was 1 astronomical unit. It's like 1 squared over 1 cubed. It just ends up being 1. Going up here, t squared over 2 AU cubed. I'm going to cube this. So it's going to become 8. So t squared becomes, I'm going to drop the units, 8. So the period of the planet, I got to take the square root and drop both sides. Period of the planet is the square root of 8. And we're dealing in Earth years, because those are the units we started with, Earth years and astronomical units. It's going to take longer to go around the Sun for this planet as it does for Earth. What is the square root of 8? It's about 2.8 years. Makes sense because that's farther away. And we said when the planet is farther away, it takes longer to go around the Sun. In this case, it takes 2.8 Earth years to go around the Sun. The last one is false. You can work it out yourself, but you would use the same process as shown here. How long does it take Mars to complete one orbit around the Sun? The distance of Mars from the Sun is approximately 1.5 astronomical units. Let's do this again. So we're going to do t squared. Again, this is Kepler's third law. T squared over r cubed for Mars has to be equal to t squared over r cubed for Earth. These always have the same number. We're looking for t, the time that it takes for Mars to go one orbit around the sun. We know the distance is approximately 1.5 AU from Mars. So t squared over 1.5 cubed. We do the same thing on the side for Earth. 1 Earth year divided by r cubed for Earth. That's 1 AU. That's 1 AU. Solving for t squared from Mars, I'm going to bring this over to the right-hand side. By 1 AU squared. 1.5 cubed is 3.375. And if I divide that by 1 AU cubed, that just becomes 3. So divide by 1 Earth. Now I'm going to take the square root of both sides. Period for Mars. If I take the square root of 3.375, 1.84 Earth years. Again, it makes sense. Mars is a little bit further away from the sun. It's going to take a little bit longer to go around the sun. Now we've been talking about planetary motion and the planets moving around the sun. We said that the orbits of the planets are ellipses. If I just look at it like a almost a circular path around the sun. For example, here's Earth. We said, hey, in order for it to be going in a circular path, it must have some centripetal acceleration here. If there's a centripetal acceleration here, there has to be a centripetal force. What is the centripetal force here for planets? Well, it's the gravitational force between the planet and the sun. Or it could be between the planet and its moon, for example. And Newton actually built upon what Kepler found in his data, in particular his third law. I won't derive it all. But he built upon what Kepler learned in his third law about the relationship between the period and the distance from the sun. And he came up with the law of universal gravitation. And that's shown right here. The gravitational force between two objects. I'll subscript G here to remind us that it's the gravitational force between two objects is equal to capital G m1, m2 over r squared, where m1 and m2 are the masses of the objects. R is the distance between the centers of those two masses. And this capital G is called the gravitational constant. It's different than little g, 9.8 meters per second squared. This gravitational constant is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. It is a proportionality constant. So if I graph Say, for example, I graph force on the y-axis, and I graphed m1, m2 over r squared x-axis. The slope of that line would be the gravitational constant G. It's a very small number, notice. 6.67 times 10 to the negative 11th is really small number. So you only really notice the force of gravity between two objects when the objects are really, really, really massive, like planets. Of course, it's always there. There's always a force between like you and me, or in any objects with mass have gravitational forces acting between them. But it's such a small number, it's negligible in the case for everyday sized objects. But for big masses like planets and suns and moons and stars, this gravitational force can get pretty big. And it causes the centripetal acceleration to occur. Now, the gravitational force is an attractive force, and it lies along the line joining the centers of the two masses. So if this is mass 1 and mass 2, the gravitational force between them is called F1 or F2. F2 would be the gravitational force on mass 2 due to mass 1. And F1 would refer to the gravitational force on mass 1 due to mass 2. It's the same size force. This is an action-reaction force pair. It's the same size force, just opposite direction. Conceptual question for you. Suppose we have 3 equal masses are located as shown. What is the direction of the total force acting on M2? To the left, to the right, total force is 0, or is it impossible to determine from the figure? Pause the video, think about it for a second on your own, and then we will discuss. Correct answer here is to the left. So M2 is going to have 2 gravitational forces acting on it, one due to M1 and one due to M3. M2 and M1 are closer together, right? So because they're closer together, the distance between them R is small. The gravitational force is big. And it's attractive, so it's going to point that way. Now, if I look at the gravitational force between M2 and M3, they're further away from each other. So R becomes larger. That means the gravitational force becomes smaller. And it's, again, pulling that way because it's an attractive force. M2 is going to be attracted to M3. So if I add up these two forces, one are to the left and one to the right, the total net force is going to be to the left. Review question for you again. Choose all of the following statements that are correct. There is a net force acting on planet Earth. The sun exerts a larger force on the Earth than the Earth exerts on the sun because the sun is bigger than the Earth. If the distance between 2 planets is doubled, the gravitational force between them is halved. If the masses of 2 objects are doubled, the gravitational force between the 2 objects is doubled. Gravitational force between 2 ordinary sized objects is very large. Pause the video, decide which statements you think are true, and then we will come back to discuss. The only one that's true here is the very first one. There is a net force acting on planet Earth. The gravitational force of the Earth, of the sun, acting on the Earth. Now the Earth experiences gravitational force between other things too, right? There's a gravitational force between the Earth and the moon, and between the Earth and even other planets, but the largest one is from the sun acting on the Earth. And that is the force that's causing the Earth to move in an almost circular path around the sun. The rest of these are actually false. The sun does not exert a larger force on the Earth than the Earth exerts on the sun. The gravitational force is actually the same on both. The Earth exerts a force on the sun exerts a force on the Earth. They're equal and opposite in direction. The sun doesn't accelerate towards the Earth because it barely would, because the sun's mass is so big that force is not going to cause an acceleration on the sun. If the distance between two planets is doubled, the gravitational force between them is halved. This is actually false due to the fact that Newton's law of gravitation has an r squared on the bottom, right? So if I double the distance between the planets, you got to take into account that that force is inversely proportional to the square of the distance. So if I double the distance, the force is going to become 1/4 as big. If the masses of the two objects are doubled, the gravitational force between the two objects is doubled. Actually, that's also false. If masses of them are both doubled, then it's going to be 4 times as large as the original. And lastly, the gravitational force between ordinary sized objects is actually very small. Because this gravitational constant, capital G, is a really, really small number. Last practice problem. You're asked to find the gravitational force. Suppose we have a person, 50 kilograms, standing on the Earth's surface. The radius of the Earth is 6,370 kilometers, and the mass of the Earth is 5.98 times 10 to the 24th kilograms. Find the gravitational force on the person, or their weight. That's another word for gravitational force on the person, using gravitational acceleration and Newton's law of universal gravitation. If I use gravitational acceleration, the weight of the person is equal to their mass times the acceleration due to gravity. And the weight is force that pulls down on the person. Their mass is 50 kilograms, and the acceleration due to gravity is 9.8 meters per second squared. So using what we've learned before about weight, their weight is 490. Their weight is a force, so this is going to be in units of newtons. Now let's use Newton's law of universal gravitation to find the gravitational force between the Earth and the person standing on the Earth. Newton's law of universal gravitation is capital G m1 m2 over r squared. We know capital G is a constant. Let's call m1 the mass of the person, 50 kilograms. M2 is the mass of planet Earth, right? We're trying to find the gravitational force on the person due to planet Earth. So these two masses are the mass of the person and the mass of the Earth. M2 is going to be the mass of the Earth, 5.98 times 10 to the 24th kilograms. And R is the distance between the two objects' centers, right? So if I just make a really crude drawing here, I'll do it over here on this spinning thing. The distance between the center of the Earth and the center of the person is basically the radius of the Earth, 6,370 kilometers. Adding that little bit of extra for the distance to the center of the person isn't going to make that big of a difference, so we won't include it. So the radius, the distance between the centers of the two objects, is 6,370 kilometers. I want to put that in meters. $6,370,000. So let's plug in our values here. G, the gravitational constant, 6.67 times 10 to the negative 11th. Mass of the person's 50 kilograms. Mass of the earth of 5.9 times 10 to the 24th. And R, 6,770,000. And I don't forget to square. If we plug in the numbers, get 491 newtons. That's a relief, because whether I use gravitational acceleration to find the person's weight, or if I use the law of universal gravitation to find the person's weight, I should get the same thing. Both of these is the force of the earth acting on the person, right? The gravitational force of the earth acting on that person. It's 490 newtons. Newton's law of universal gravitation is actually more universal, right? You can use this anytime, anywhere, right? This one on the top, weight is equal to mg. That's only working whenever you're standing near the surface of the earth. As soon as you get far away from the surface of the earth, this equation breaks down and doesn't work anymore. And that's when you need to revert to using this universal law. All right, so we have applied, we've gone from going around the bend in your car to finding the gravitational force of a person and calculating the periods of Mars. So that's the beauty of physics, right? You can apply basic principles to many different contexts, which is that's my review of chapter 5. I hope you enjoyed it. Thank you so much for hanging in and listening.